Good to see you again, scholars. Welcome to Chemical Reaction Labs or Unilab Virtual. Today, we are going to be looking at data analysis on saponification of ethylacetate in series CSTRs. But before we delve into it, it will be interesting for us to consider the characteristics of continuous state tank reactors. The continuous state tank reactor is a closed vessel where reactants are continuously fed and products are continuously withdrawn. Its characteristics are: 1, it maintains a well-mixed environment using steering mechanism ensuring uniform reaction conditions. 2, it offers steady state operations, making it suitable for large productions and reactions with long reaction times. 3, heat transfer is commonly achieved through a cooling or heating jacket surrounding the reactor. And lastly, it allows for easy control of operation parameters and ability to handle multi-phase reactions. Like I said, today, we are here to explore data analysis on saponification of ethylacetate in series CSTRs with sample calculations and analysis. Before we write it, I would love us to review the background knowledge, which includes the aim and objectives and theoretical background for this experiment. This will drive our direction for data analysis and foster our discussion. Good. The aim of this experiment is to study the influence of the steering time on the conversion process in the state tanks in series. The objective of the experiment is: 1, to measure conductivity as a function of time for the CSTR in series, to determine the relationship between the conversion and time for the CSTR in series, and to construct the cumulative distribution and resident time distribution curves for the reactors. It will be interesting for us to look at some equations and background that will show us to compute the cumulative distribution function at seen equation 2.3 to equation 2.5. Equation 2.6 express the residence time distribution function, and equation 2.7 express the mean residence time, Tm, for the reactors. We can see that we applied the Simpson rule for computing the mean residence time for the reactors. The experimental result is depicted in table 4.1. Here we used a time interval of 3 minutes. Your experiments can differ from mine. You want to use intervals of 2, 3, or 5 minutes, depending on your instructor. We tabulated the conductivity values of reactor 1, reactor 2, and reactor 3 against time. We have the sample calculation for cumulative distribution function, which is f of t for reactor 1, C out over C naught, which is 30.2 over 0.18, giving us f of t equals to 167.778. Also, you can see the sample calculation for residence time distribution function, E of t, for reactor 1. Here, like we saw in the theoretical background, this expression helps us to determine the E of t, and then our E of t is 167.77 over 3 minus 0, which is 55.926. Other sample calculations are shown here for mean residence time, wherein the curves for the cumulative graph is separated into 2 segments. As shown in this graph, we can see that this very curve, starting from here and ends here, then continues to drop down here. We are going to take our first integration from here to here, and then take our next integration from here to here. So that's why we have this expression. So for n plus 1 point, where n is even, we have this expression. Then our h, which is the height or step, is given by Tn minus T naught over n. So from 21 minus 0 all over 7, which gives us 3.0. So if you go back to the expression, if you go back to the table that we use to obtain T, Et dt, we can number them from f of 0 to f of 8. The values of these functions were taken and all the f of even numbers were added here times 4. F of the odd numbers were added here times 2. This is the initial f and this is the final f. And then we compute it to have Tm equals to 3,319.445 minutes. They are moving to Simpson 3H rule 4 points. We compute the second segment and then we obtain Tm equals to 568.33 minutes. Therefore, the value of the integral Tm is the addition of the two Tm's. You can call this Tm Tm2 and call this Tm Tm1. So our final Tm for reactor 1 is 3,887.778 minutes. Now our analysis has produced this table. This is table 4.2, cumulative distribution f of t and residence time distribution E of t. We can see it here. This is our Tm1 and Tm2 sums up to give us Tm for reactor 1, reactor 2, and reactor 3. And then we can see the values for the f of t and the E of t. The values that we use for the t times E of t is f of t, owing to the fact that our t times E of t is the same as f of t. We can see it in this equation here that our f of t equals to t times t minus t naught E of t. So if we take a point value or a instantaneous value, it's same as f of t equals to t times E of t, because the t naught is equal to 0. So that's what we use to compute this. We also generated table 4.3, which is conversion of reactants versus time. We have to plot graph of conductivity against time for CSTR in series, also construct the residence time distribution function for the reactors, analyze the curves to understand the performance of the reactors, and plot graph of conversion against time for each CSTR in series. As depicted in figure 4.1, we have a graph of conductivity versus time for the reaction, showing each reactor 1, 2, 3, and then we have figure 4.2, residence time distribution, and other figures that are plotted as expected. So figure 4.3, cumulative distribution function versus time. You can see in figure 4.2 that each of the reactor's residence time functions is displayed on the graph. A bell-shaped curve. A bell-shaped curve is visible in all reactors, with reaction 2 having the most extreme leftward skewedness, followed by reaction 3 and then reaction 1. In your discussion, you have to analyze your results in the context of the objectives. Examine the effects of step input in CSTR in series, discuss pattern and trends, compare your finding with existing literature. Now, I want us to look briefly into the things we might likely discuss in this experiment reporting. The primary aim of this experiment is to examine the reactor's conversion rate and performance by measuring the residence time of continuous state tank reactors in series with step change inputs. Gantt models CE 310 continuous state tank reactors are utilized to investigate this impact. The component of the effluent that has been in the reactor from time t equals to 0 minutes until time t equals to t minutes is represented by the cumulative distribution curve, FT curve in figure 4.3 as displayed here. An experiment's FT value is calculated for each experiment by dividing the concentration of the tracer value C of t at t equals to t by the initial concentration of the tracer value C naught of t at t equals to 0 minutes. In comparison to reactors 1 and 2, F of t cost for reactor 2 indicates that the CSTR mixing is the closest to ideal, as seen in figure 4.2 and figure 4.3. The FT cost for reactor 2 spikes sharply at around t equals to 15 minutes. Possible causes include dead time volume or stagnant area inside the reactor, which impede fluid flow. And the F of t curve for reactor 3 is quite similar to the F of t curve for reactor 2, because the presence of a metal coil inside the reactor may cause stagnant area or dead volume. In addition, the mixing behavior may be affected by the placement of the impeller or stirrer within the reaction. There is a higher probability that stagnant area exists within the reactor due to metal coil. Differentiating the value of F of t, use the residence time distribution function denoted as E of t. The quantity of time that various fluid components are spent in the reactor is shown by E of t. Since the flow curve in reactor 1 declines with time, it is the most perfect CSTR as shown in figure above. In contrast, reactors 2 and 3 have bell-shaped curves. In contrast to other two reactors, reactors 2 ET's curve has the greatest value across all values, indicating a higher rate of mixing. The residence time distribution function takes the mean residence time as the initial point. The average amount of time that fluids remain inside the reactor is shown at this moment. Figure 4.3 shows a time versus TET curves. The numerical integration methods use the area under the TE of t curves, which is used to compute the mean residence time. The value of the mean residence time is the total area under the curve. Reactors 1, 2, and 3 all had mean residence times of 3,887.887 minutes, 5,383.214 minutes, and 4,864.297 minutes, respectively. According to the experiment, reactor 1 has the shortest mean residence time. It is likely because the metal coil already takes some room within the reactor. There is dead time volume, stagnation region, and the fact that the space is already in use means that the fluid cannot remain much longer. Because of this, the ability to flow uniformly within the reactor is impaired. Regarding reactor 1, the fluid takes more time to reach the effluent stream due to the central situated impeller, which limits its velocity, and consequently, the residence and mixing time in reaction 1 can be extended. The positioning of the impeller closer to the top and bottom of reactor 3 results in a decreased residence period compared to reactor 2. Figure 4.4 shows conversion of individual reactor versus time in minutes. Maximum stirring rate was used in each reactor to make the energy needed for conversion available. Dead time concentration was the lowest, having the least initial concentration of the reactor. And with time, other individual conversions converge. Of the three CSTRs, reactor 3 has the highest overall conversion, affirming Ca3 equals to Ca naught over 1 plus K tau into bracket raised to power 3, where Ca3 of reactor 3 is less than Ca3 of reactor 2, Ca1 of reactor 1, and Ca naught overall initial concentration. Thank you. A few texts, which are Fogler 2006, Adeyemo 2023, Rochelle Fori 2016, and all referenced in APA style. Thank you for watching data analysis on saponification in chemical reactors for undergrads. If you learned something new in this video and you derive great value, please like the video, subscribe, and share for more valuable content. You can also comment and ask questions on this topic and any other related engineering topics. Thank you. This tutorial is powered by UniLab Virtual. See you in the next episode.